Today is going to be about Solr Compute Cloud, kind of like an elastic Solr infrastructure which we built in-house to fit BloomReach's search use cases and scaling needs. So just an FYI before we start, it's close to a year's worth of work which I'm trying to talk about in 30 minutes. So we'll try to put at a very high level, and some of the low-level details will follow. But if you want more details about this or anything, please email me or come find me offline. I'll be more than happy to chat about it. So let's go on. Abstract, at a very high level, what are we trying to solve, right? Like every other company, BloomReach has its own search use cases. That could mean you need to have always serving architecture, which needs to have a certain SLA that needs to be met for latencies, for stability, for uptime, as well as with the number of growing collections that you have and the number of document growth, the SLA needs to stay at the same level. So that's one of the major use cases which we have. And a few others are, how do you have heterogeneous workload in your system while guaranteeing SLAs? When I mean heterogeneous, what I mean is you have multiple read pipelines, some of the direct queries that are coming to the front end, as well as indexing. A lot of indexer jobs could be partial, could be full-time indexing, whatnot. So with all these kind of complicated workload, how do you still manage to have a certain amount of uptime and certain amount of stability and performance in your infrastructure without losing the stability of the infrastructure at all? So what we did is we tried out a few different things, as I'll be mentioning as we go forward in the presentation. We tried to build our own cloud infrastructure internally, primarily based off Solr Cloud, that helps us achieve all of this in a much elastic fashion. And when I mean elastic, it automatically grows or shrinks based on what the demand is, so that you don't have a single provision cluster that is large enough to hold the peak. At the same time, it's not too small enough so that your average load does not get handled. So it's more like provision for the average itself so that you optimize cost. But when you have peak, you can dynamically grow your infrastructure so that you can meet your SLAs. So about us, as I was mentioning, I was from BloomReach. BloomReach is a big data-driven marketing platform. We offer a variety of products and applications to our consumers to make their own content discoverable, more searchable, and much more relevant. And it also helps identify opportunities in optimizing their site. So I'm Nitin. I've been working for search-related stuff for about 2.5, 3 years right now. I've been with BloomReach for close to a year and a half. So primarily my work is regarding search, latency-sensitive applications, as well as performance debugging. So BloomReach offers 3 different products right now. One is for search. How do you optimize the search in your website and personalized search? Another is Compass, which is basically our opportunity identification mechanism for our customers. It's a summary of what I was just mentioning in the last slide. So what can you expect from this talk? What are search use cases into a much more granular level for what BloomReach is doing? What was the old architecture like? How do we start? And what we learned along the way, and how did we actually re-architect the system to fit our use cases? So again, some of them may be at a high level, at a lower level, but please come and find me offline if you have any more questions. So search use cases, just like any other search, the first one is purely latency-sensitive front-end applications. We have a public API that is serving real-time requests coming from the consumers. So at any point in time, for different sets of complex queries that you are getting, including faceting, custom query components that we have written, whatnot, all of them need to be satisfying a certain performance SLA between, let's say, X milliseconds or X seconds, or with a certain amount of QPS that is given. The second thing is the most important thing that we have is since we have multiple applications, every application needs to do its own kind of analysis and relevance to find out its own output. So what I mean by that is you have a large amount of ETL pipelines. They have a different input and different output that needs to be produced. The output definitely needs to be a lot more relevant. So when you come into relevance and text, you already need to have Solr in place for that, because it already gives you a good platform for that. So our number 2 is a very big use case for us, because you have a lot of pipelines accessing Solr in different times to get the most relevant content for them. And 3 and 4 make the things even more hard to achieve, which is our customers would say, I would give you data X, and it needs to appear in time Y. So it's becoming time-bound, which means that it's not just enough to get your pipelines working. It needs to make sure that you give a guaranteed SLA for the pipeline to finish. If it starts at 10 a.m., it better finish at 10:05. I'm just throwing out numbers, but it's that kind of a thing. And we also have not only just indexing, but we have a lot of custom configurations inside Solr for all the custom components and external files that we use. So all of these need to happen in a very, very time-bound fashion. So that makes the problem even more harder. So this is the old architecture. This is how we started off with, right? Typically, it's more of a pictorial representation of what I was talking earlier. So you have a huge Solr cluster in between. We started off with 4.3.1. Now we are at 4.6, but we will evaluate the future versions as we get time. So we have a Zookeeper ensemble, and we have a lot of indexing pipelines running throughout the day at different schedules. And you also have a lot of read pipelines, purely MapReduce based. So you can imagine the load that they would bring in. And you have a public API, which is also serving real-world traffic. As you can see, some of the pipelines are very heavyweight. Some of them are not so much. But the harder problem is all of them could run at any point in time. So it makes your infrastructure almost unpredictable as to what its performance or stability would be. So let's get into the problems of what all issues that we saw. First is the throughput issues on the read side, right? So the red circle, at least for the next couple of slides you see, that is the actual bottleneck I'm talking about, just to let you know. So throughput issues, what kind of issues we had were that first is you have, let's say, 10 pipelines running at the same time. Some of the collections inside Solr for us are very large. Some of them are very small. So when you have such a different kind of mixture, what happens is, let's say a larger pipeline and a smaller pipeline at the same time, the smaller pipeline could get starved. A larger pipeline could be issuing a lot more queries that might utilize all your infrastructure, CPU, memory, and everything else. So that could make your smaller pipelines runtime either larger or smaller, or it could eventually lead to starvation. So that was one of the major things, which added up to the earlier point which I was making, saying that we need to guarantee a runtime for every pipeline, and this actually makes it very, very hard. So second thing is actually the most interesting one. The same collection in Solr is getting queried by different sets of pipelines. So what that means is even though, so let's say there are 10 pipelines accessing collection A, and you have only, let's say, 2 or 3 replicas for that, that becomes a problem because you have only 3 concurrent sources that you can read the data off of. So that becomes sort of a problem. And if you want to add more 10 replicas or like 15 replicas for the same collection, that becomes way more costly because you need to add more machines. Yes. Pipeline is a MapReduce job that cascading pipeline or like a bare Hadoop pipeline that just hits Solr for its queries relevant to it and then gets the results out. Yes. So that becomes a harder problem because multiple pipelines access the same collection at the same time. Cache tuning, actually cache gives you, in Solr gives you, for serving use cases is very, very effective because you can get different kinds of performance benefits out of it. But imagine different pipelines having different query patterns accessing the same collection in production, you're not going to get that much out of cache. You see a lot, we actually saw a lot of misrate in cache and evictions than anything else. So that kind of a shared infrastructure for this did not give us anything out of it. And 3 and 4, actually the last one is the most important thing that we had, which was giving us trouble, is there's no isolation among the jobs. And what I mean by that is, first one was starvation. A larger job could just eventually make sure that your smaller job never completes, or if a larger job gets stuck in between, freezing up all the Solr threads, at that point your smaller job will never complete, smaller job at all. So there is no isolation. If you have one misbehaving job that is bombarding your cluster, then the other jobs also get stalled. So there is not like a pure isolation between the jobs, which makes scaling this even harder. Okay, second part is the cluster itself. So imagine what will happen. You have all your pipelines and your indexing jobs directly accessing your cluster. So this could open up to so many other issues. Bad clients is one of the things which we were bitten by so many times. Somebody writes a bad client, which just opens a lot of threads. They do all unoptimized queries. For example, some of them were not using filter queries correctly. They were just using Q equal to all the time, which has utilized the system memory and system CPU all the time. So if you have a bad client coming in and opening up all your threads, then instead of the job failing, the cluster fails. So that at that point in time, you're basically done. It's going to take a lot of time for us to reindex all the data and things accumulate. Number 2 and 3 are primarily regarding the memory utilization of the cluster itself. Because indexing and pipeline have the exact same amount of memory and CPU load, what happens is you run into all sorts of garbage collection issues. Like you have a memory-heavy job for reads as well as memory-heavy jobs for writes. So it doesn't matter how much of memory you give. Actually, the more memory you give, garbage collection becomes even worse for you. And tweaking that specifically in a shared cluster when you don't know what is running at any point in time, it actually caused so much problems for us. We also ran into a bunch of issues with Zookeeper because our data size grew more than 1 MB. We had to fix our jute max buffer size, and traditional problems with performance wherein we were putting both our transaction and the data logs in the same drive. That did not give us that much performance, so we had to split that out. So, and all of this we had to learn through crashes. So every single thing we had a crash before we had a big lesson that came out of it. Now let's go to the indexing side of it. What are the issues in a shared cluster with indexing? The commits. Commits is a very big problem for us because since we have time-bound pipelines, everything needs to finish within a certain amount of time. So pipelines just tend to do all kinds of commits. Some of them do hard commits, some of them do soft commits, and the frequency of commits becomes varied between the pipelines. So one of the things which we tried to do was do auto commits from the server side. It helped us to a certain extent, but still nowhere close to where we wanted to be in terms of isolation or in terms of guaranteeing what the times are. The last two are my personal favorite. Too many stored fields. We were using Solir as a database at one point in time. So instead of using a proper database where you can have a key-based lookup, we were storing most of the data in Solir itself. So that slowed down the performance of Solir, and that almost the indexing time went a lot higher. So this, we did a big analysis to figure out how this could actually be done another way, where you can actually query Solir for just what you need, get the key, and then do another actual database for lookup or scan or whatever you need to do. Another thing is we don't have any kind of rate limiting among the jobs because that's another infrastructure which we need to maintain and which we didn't have time or resources for. So given all of this in place, it was clear to us probably about a quarter into it when we realized that a shared cluster does not work for us. This is not really giving us anything, and it was taking so much of time firefighting instead of actually building something nice. So we thought, let's summarize what are the learnings that we've got out of it. Shared cluster does not scale. When you're a search-based company and you're having close to 99.99x terms of uptime, this kind of architecture does not scale for us by whatever means, because even the smallest of mistakes, either in the infrastructure or on the client side, could just bring down the whole system, is not acceptable. If you run a pipeline against Solir, it works. If you run 5 pipelines at the same time, it breaks. So something has got to do with isolation. So if we are able to isolate the job into running its own cluster, then maybe things will work out. You don't need to worry about the infrastructure itself. But how do you get things to run in isolation without having any direct access to the cluster? So that's when we ran into a sort of an experimentation. We spent a couple of weeks seeing if we can create a cluster on demand for every pipeline, just give it the collection it needs. Let's say you have collection A all the way to Z. A pipeline comes in and it says, I want to run a job against collection A. It doesn't even need to have collection Z in the place. And it doesn't need the data at all. So why not have a certain way of saying, okay, we are going to guarantee isolation, but every job gets its own cluster. So that's what led us into what we call Solir Compute Cloud. It's a completely elastic Solir infrastructure. So what we do is every time a job comes in, we provision a cluster for the job for Solir and give the job that cluster alone. The job can do whatever it wants against that cluster. It can read, it can write, it can request as many replicas as it wants on the fly. And once the job is done, it can just kill. So in this way, what will happen is you are getting from a provision for the peak model into provision just enough for the average model. So you have a static cluster just enough to hold your real-world traffic for the SLAs. At the same time, if you have, let's say, someone accidentally goes and creates 1,000 pipelines and forgets to kill all of them, and they're running all the time, all of them get their own cluster. And if they kill only their own cluster and not production. So this gives us a very, very good way of protecting production from a job-specific issue that could occur. So what makes us do this is 2 technologies which we built in-house. First is something called the Cluster Management API, or we can even call it the SE2 API. What the API does is it creates clusters for you. It creates Solr clusters for you, and it does it in an optimized fashion. So based on what the collection is and how many replicas that you want, we figure out how many machines that are needed, how many resources that are needed, and we create a cluster for you at that point in time. And the second is Solr HAFT. I will get into that a little bit detail in the coming slides. But what that is, it's a homegrown library for Solr which we wrote. It offers a whole bunch of functionalities, from disaster recovery functionalities, from cluster cloning, from replication to everything. But in this context, it primarily provides a huge replication functionality. What that means is you give it a source Solr Cloud cluster and a destination Solr Cloud cluster and ask it to say, hey, copy me all the data from A to B. It will do that for you. It does some complicated stuff on top of it, but at a higher level, that's what it does. It gives cluster A, cluster B, say, copy all the data from A to B, it'll do that for you. So given these two, now we have the ability to say, I can create any cluster anytime, I can copy any data I want. Now, why not do that and put it into practice? So this gives us the three main things that are needed for our use cases, which was mentioned earlier, which is job level isolation, everybody gets their own cluster, and nobody kills production, dynamic scaling. Let's say you get 1,000 or 2,000 or 3,000 jobs coming up in the future, or someone says, I want to run all of them. It's the holiday time. I want to run more jobs to get more analysis. You don't just bring down production. You just scale dynamically based on the demand that is coming in. Cost saving, again, this is from the production standpoint. Now, an incoming cluster, if it requests 6 replicas, I don't need to create 6 replicas in production. I just need to create it with 2, maybe for failover. And then the copy library will take care of expanding 2 to 6 dynamically. So this actually gave us much more breathing room, as well as a lot of sleep at night to get into it. So let me walk over the actual. Yes. Okay. Okay. So let's get into the view of it, right? A pipeline comes in. In the previous model, it directly accesses Solr. Nobody puts any access restrictions. This is how it will be in the new flow. Pipeline comes in, it calls the API, and he says, give me collection A with 6 replicas. I want to finish it in 10 minutes. And the API now provisions a new Solr cluster, and it copies, and it uses the Solr HAFT service to copy the data for collection A from the production Solr cluster onto the Solr cluster dedicated for the pipeline itself. So now what will happen is, now since the pipeline has got its cluster, it'll run the job against the cluster itself. So this will safeguard the production cluster, as well as you have your own resources in your own fashion. So the pipeline now gets a view as though it needs all the replicas it just wants. It has its own way of working with Solr. The second one is, let's say a job finishes. What does it do? Exact same thing, but on the reverse flow. It calls the API, and it says, hey, I finished my job. Terminate the cluster. So the API does the same thing by just terminating the cluster. And at this point, HAFT is not used because it's just a killing the cluster perspective. So putting it all together for the read view. If you look at the original diagram, there were 3 views, stability view, the read view, and the write view. So if you look at the read view now, every pipeline that comes in calls the API, gets its own cluster. We use the HAFT service to copy the data from production onto a dedicated cluster. All the jobs run against the dedicated cluster, and they terminate the cluster whenever they are done. So this provides almost linear scalability for us at any point in time. You throw more money at that cluster, you probably get a better thing. But the good point is now we're heavily based off EC2, so we use Spot instances for most of the stuff here. So what we do is we pick the cheapest Spot instance at that point in time. We run the job against it. We create that cluster. And then we terminate it once it's done. So these are not long-running clusters by any means. There are a few other optimizations which we did, which I will stick to the end of the presentation because it's a little more complicated. I just wanted to get through the majority of the parts now. Now, let's get to the other side of the picture. What will happen in indexing? It does the same thing. It requests the cluster. It says, give me collection A with probably lesser replicas because indexing, it's better with a smaller number of replicas. So it gets a collection with A with 2 replicas. And now what it does is it does the job. And now instead of just terminating the cluster, the indexing job will call the HAFT service and say, hey, I'm done with indexing. Copy my data into production whenever you need. So at this point, we actually provide helps us in 2 ways. First thing is, now the only production operation that is allowed, in the production cluster is replication. There's no reads, there's no updates whatsoever. We replicate from production outside, and from outside world into production. So that and Solr replication is really, really rock solid. And we have built most of the libraries on top of that itself. So there is no unpredictability. If we know that Solr replication is going to take X seconds, it always takes X seconds based on the resources that you give it. So now what will happen is we can do more heavyweight operations. For example, one thing which came up was the old master-slave model, right? If you optimize the index on the master, and the entire replica needs to get, the entire index needs to get fetched to the replicas. So that might cause some bumps in the latency. In this model, what we'll do is we do all the heavyweight operations on our own cluster. We do the optimize that we want to. We want to split the shard, we split it. Whatever, all the heavyweight operations are done on that cluster, and we just call this library to just copy the data over. So the whole point of reads and writes now just becomes a point of just replication itself. So this actually has improved our stability and uptime by a lot. And now we're pushing through more requests, almost more than 10 to 15x the requests that we were supporting in than the older model. Pipelines that used to take more than half a day or a couple of days to finish is now finishing in a matter of hours because everybody has its own cluster. You mean overall, or?
Yeah, when you bring up into cluster, you have to copy the data, right? So how much data and how much time? And when you do indexing, you copy it over again to production. That's downtime for your production.
No, it won't.
You said that no reading, no writing going on, just a replication.
I will come to that in a bit. So, but anyway, the answer to the question is, when you copy the data, it depends on the collection size that we have. Some of them, I can't give you the actual number, but I can talk to you offline about it. In production, we do something else. We use aliasing in a much smarter way. Instead of having aliasing supports collection 1, 2, and 3, where you can say that you can, instead of querying 1, 2, 3 separately, you can create an alias. So what we do is it's a work in progress, but that's the plan that we want to do is when we copy the data over, we don't copy it to the same collection. We copy it to a new collection, and we flip the alias. And we can delete the old collection back. So this will help us avoid the downtime, which we are talking about. The separate cluster? Yes, I should have mentioned that. They have their own zookeeper. It's usually in the same node itself because it's a short-lived cluster. Yes. Okay. So this is the global view, putting reads and writes together. You have production, you have a HAFT service, you have the API. Anybody who comes and requests a cluster, we use the service to read and write data back, and then now you have a new layer of elastic clusters which grow and shrink based on whether a pipeline is coming or not. And the most good thing about all of them is nobody touches production directly, which we can sleep a lot at night right now. So again, this is just summarizing what I was saying earlier. You have an API to provision the clusters. It's a dynamic way of growing and shrinking. Since we use EC2, we do a cost optimization to say, let's not provision more than X amount of nodes for this cluster. That's getting requested right now because then the infra team would come back to us and say, you're spending more money. Track request state and performance. So it's not only, it's not a stateless in the true sense, which is because if it gives a cluster back, it needs to keep track of what is there. So in case it becomes a runaway instance or someone fails to call the terminate on you, you better keep track of it and you terminate long-running jobs or long-running clusters. So HAFT service, it's a short form for high available and fault tolerance. It's a homegrown technology. We built it probably 6 or 7 months ago. The plan is to open source this. The work is in progress right now. If things go as planned, then probably sometime early next year I will get to that. The features as such, I was talking on the HAFT service purely from a replication standpoint earlier. But if you look at it, it provides a whole bunch of things. Like our entire disaster recovery mechanism for the Solr cluster is built through HAFT. I will get to that in the next slide to actually give this whole power of saying how does HAFT come into the picture to give you the uptime. Because we've seen performance, we've seen isolation. Now the only thing remaining is uptime, and I'll get to that after this. So some of the high availability operations is, let's say you have a 100-node cluster, one node goes down. You don't create another cluster. You create another node, but in this case, this library helps you create another node, recreate all the cores in that node itself. Now the cluster will be back to form as though it was originally, as though nothing happened. Collection versioning is what I was mentioning about. We use aliasing in a different way, and by different I mean instead of chaining all the collections together, we create a different version of the same collection, and then we flip the alias to that collection, and that way you can do things like quality checks. You have a version 1 of index and version 2 of index. You don't want version 2 to go live instead of version 1 because you want to do some quality checks on that. We do that, and then we flip the alias based on that. So we use aliasing in a different way completely. Cluster backup is what I was mentioning. Now we have the ability to clone the collections from one to the other, right? So this could open up a whole bunch of things. Given cluster A is burning down. I can just use the service to copy all the data of whatever I could into that, and then reindex the ones that are remaining, or whatever needs to be done. For the most part that I've used the cluster clone, it's been flawless. It is directly proportional to the number of collections you have, but the streaming is super fast. So it's been of great help to us. So if you look at the HAFT as a functional view, these are the three major things that it provides. First is index management. It does optimize. It clones the collections. It clones the alias. There are a few high availability actions which I was talking about, which is, let's say a cluster is burning down. We have something called black box recording. What it does is it just calls the cluster. It tries to collect as much information from the cluster as possible. What is the state of every core? How many documents are there? Is something going down? What's the memory of every single system? And a lot more details to that. We have actually one more thing which I failed to mention is we have a lot of custom components, as you might have imagined. That's where the latency tuning part becomes harder. So we collect a lot of data from our custom components as well to see, if they can be reconstructed or not. Node repair and node replacement is what I was talking about. The major things are the cluster backup. So cluster clone and cluster swap. So cluster swap is more like saying, I have a cluster A, it's burning down. Now I use cluster clone to create cluster B. Now make B the production cluster. So we have a whole bunch of internal systems that operate either based on DNS or some other mechanisms. Now we need to make cluster B as production. So we just maybe like flip the DNS or update the internal entries, or have other services that are using this use the new cluster instead of the old cluster. So we have something called, the next is state reconstruction. So in case your zookeeper data goes corrupt, out of 3 zookeepers or like 5 zookeepers, 2 of them go down and 3 of them are there, but you're still worried about if any of them else also will go down. So what we do is we take that zookeeper data, we reconstruct that state from that zookeeper and create a completely new cluster based off that state itself. This is not only helpful in production, but it's also be really, really helpful when we are doing the testing itself. So let's say we want to push out a new component change or a new code change for the API or for this, we can do all sorts of stuff. And destructive testing also becomes simpler. All we have to do, let's say what will happen in your production if something goes down, we can just reconstruct the state, and we can do all kinds of funky destructive testing. So there's a guy on PagerDuty. This is almost most of the time that we are on. And everybody is on PagerDuty in a rotation. So what happens is we have the production cluster, right? So something goes wrong and the guy gets paged. What did he do previously is we used to manually create a cluster. We reindex all the data, and that reindexing takes hours or days depending on the number of collections we have. Now, after the HAFT service, how our life has changed is it's as simple as this. We have a PagerDuty guy. We have a push button that goes and says, hey, create a new production cluster. That's it. What it does is first, he clicks on the recovery button. Number 2, the push button actually uses the HAFT service for all the other functionalities that I was mentioning earlier. It does first, it creates a cluster setup. Then it constructs the state from zookeeper, creates a new cluster. It clones all the data from the production cluster onto the new cluster itself through the HAFT service. And then finally, it does the cluster swap. So what the cluster swap is saying, hey, I've done all the verification. The new cluster looks really good to me in terms of data parity or in terms of component parity with the old cluster. Now, I just take the DNS away from the old one, and I just flip the DNS. So this process is completely automated. We have tried it many, many times. It's become so handy. And I actually, in the email list in Solr, I see a lot of people asking for this. So that's why what prompted us to actually go for the open source, which we'll get to. Okay, it's at a very high-level matrix of what we did with and without SE2. Most of the things what I was talking about earlier. No direct access. You can prevent from bad clients. You can sleep at night. You can do dynamic collection scaling based on what pipelines and what collections you want. Availability. What this opens us is something really, really new is cross data center support. Let's say you want to create, you had something in US East and you want to go to US West or something. Now, you don't have to create a complicated setup where you have a shared zookeeper between this guy and that guy indexing, writing to all these clusters. You can just use the service to copy the data from here to there. So you can have like replication setup between all the clusters running at a regular interval of time to just keep copying data between all of them at any point in time. So one cluster definitely doesn't need to know about the other cluster. If this guy dies, you can create a new one and then still keep copying the data. So actually, the cross data center support is a big win-win for us in terms of uptime and stability. So rest of it was just the functionality I was talking about earlier. You can do disaster recovery, you can do collection versioning, whatnot. So lessons learned. It's a search platform. Don't use it as a database. It didn't work for us. If it works for you, we'd love to hear about it as well. Understand the access patterns. We have multiple pipelines and so many things going on. Please be very careful. Understand that. 5 seconds. And the last piece is build the automated disaster recovery. It will really, really come in handy. So thank you so much. Thanks for the extra time.